Okay, today is the 10th lecture in the series on marine hydrodynamics, and in the last two classes we spent time in understanding several two-dimensional flows. In fact, in between I talked about how using the complex function theory, how we can represent various flows. In the process we have talked about sources and sinks, and we have seen that a sink but is nothing but a negative source, and in case of a source the flow is always in the radial direction. On the other hand, we have seen that in case of a vortex the flow is always in the tangential direction. Now, with this understanding, again we have seen that when we have seen the additive characteristics of these various sources in a flow, that is possible, and it will the individual identities source characteristics will be maintained. On the other hand, when we think of a boundary surface inside the flow, particularly we have seen the in taking a case of a cylinder, in the presence of a source, we have seen that the source additive property will not hold good when a cylinder is introduced to the flow. Now, with this understanding, today we will spend some more time on various types of flows, particularly after source and sink what happen, what is a doublet, and then we will mention few theorems, results relating source, sink and doublets, and also vortex. With this we will start. Before going further, I will keep one very important result, that is known as circle theorem, although this result I would have told much before, but let me mention this. What is a circle theorem? This theorem says that if there be a, suppose we have a rotational motion, we have a rotational motion of a two-dimensional flow, we have the rotational motion of a two-dimensional flow, and of course the fluid is assumed incompressible, and envisaged. And we are in the jet plane, particularly the compressed plane. So, we are talking about a flow of a rotational flow of a fluid where the motion is rotational and it is two dimensional in nature. The fluid is assumed to be incompressible and envisaged. So, and we are in the jet plane, basically the complex jet plane. If we introduce, suppose there are no rigid boundaries, initially we assume let there be no rigid boundary. And let Fz represent the complex velocity potential of the flow, complex potential. Potential of the flow. If Fz represents the complex velocity potential of the flow, now what we will do, if we introduce a circular cylinder, if a circular cylinder is cylinder of radius not z is equal to a is introduced into the flow, then what will happen to the new compressed potential? Then the new compressed potential becomes W is equal to f of z plus f bar square by z. So, this is part of this is the circle theorem, and this result we apply, you can apply to several results, it has several applications. This result has the simplest application is, suppose I consider a flow W is equal to uz, that means I have a uniform flow with a speed u. Then if I apply, for example, this is an example I am taking. So, this is a uniform flow where the speed is u naught, is speed of the flow. Then if I apply circle theorem, so by circle theorem, if I introduce a circular cylinder to the flow, then my new Wz will be equal to u naught z plus u square by z, and this is the, we have already, this is the flow, uniform flow past a circular flow past a circular cylinder. This is the uniform flow past a circular cylinder, and already we have derived several results on this flow in the one of our previous class. So, but it is directly coming, this result is directly coming as from the circle theorem. With this, now we will go back to sources and sinks. For another example, we know about source. I will work out another example on the source. Suppose I just consider a source in a uniform stream, a single source. So, let me consider I have a W is equal to uz plus m log z. So, this is, let me call this as u naught. So, initially I had a stream velocity, uniform flow, and I have added to that, suppose I have a source of strength m present in this. What will happen to this? If I, from this I can get what will be dw by dz. This is u naught plus m by z. So, if dw by dz is 0, which gives me my z is equal to my, rather I will say m by z equal to u naught, which implies my z will be minus m by u naught. So, that means when z is minus m by u naught, this will be this flow. So, at z is equal to minus m by u naught, there will be a stagnation point. There will be a stagnation point in the flow, and we can easily see that this point is lies on the x axis, and further it can be easily seen that what is the compressed velocity potential, particularly the streamlines. We have already seen W is equal to uz plus m log z. If you look at the complex velocity potential, so from this we can get phi plus I psi will be u x plus I y plus m log r u to the power I theta. If we put it, u times x plus I y plus m log r plus I m theta, which you can write as u x. I started with u naught, so u naught x plus m log r plus I times u naught y plus m theta. So if I look at the streamlines, psi will be u naught y plus m theta, which is same as u naught y plus m tan inverse y by x, where my r is equal to x square plus y square, or I call it z is equal to x plus I y. So if I say psi is equal to constant, that means my streamlines will be tan inverse y by x, that will be constant. These are the streamlines. This will give the streamlines. And we can see what will happen when we put y is equal to 0. If we take y is equal to 0, then that itself will give us a constant. That means we can always say y is equal to 0 will the line x is equal to y is equal to 0 means it is the line x axis, and there will be no flow which will be crossing across the x axis, means y is equal to 0 will be a streamline, and we can say no flow will cross the x axis. There is no flow across x axis. So this is an example where we see that when there is a stream and there is a uniform flow, we can have a stagnation point in the flow, and that stagnation point is on the x axis, and there will not be any flow that is above there is no flow which will be crossing the x axis, because the x axis itself behaves like a streamline. Now I will take a different example. Suppose I have a source which is, let me consider a source. I have a wall, and let me draw along the x axis. Let there be a point A, that is a comma 0, and now let there be a source of strength m at A. This is on the x axis, there is a wall. If there is a source, what will be the mirror image? Mirror image will be at minus A0, that will be on the other side. Suppose there is a mirror image, so then what is the complex potential? If I look at the complex potential, m logs z minus a plus m logs z plus a. So that means the point z is equal to, if z is equal to point A here and I have a wall, then this z is equal to minus A will be just on the opposite side of the wall. That means it is at a mirror distance, again at a same distance from the wall, and appears as if it is on the opposite side. Then it is like a mirror image. So what will happen to this? So this will also can be written as, so from here what will happen, dw by dz. If dw by dz I calculate, that will give you m. Okay, this can be, from here it will be m log z square minus a square. So when I say dw by dz, that will give me 2m by z square minus a square into, so this will be dw by dz. Then now near the wall, what will happen near the wall? We have near the wall means x is equal to 0. So what will happen to dw by dz? Near the wall, dw by dz is, this will be 2m, z is x is 0, so this will be iy by z is x is 0, so this is minus y square minus a square, so which I can call it minus 2 I times 2my by y square plus a square. And again, if you look at dw bar by dz bar, from here itself we will get 2my by y square plus a square. So from this I can get q square, which is dw by dz into dw bar by dz bar, and that gives me 4m square y square by y square plus a square square. And now, so that means on the wall x is equal to 0, this is my wall, the force, the speed will be, which will be directed towards the wall in this direction. This is the speed. At this speed the fluid will be flowing from the source. And once we have q, but since this wall is also a streamline, then we can have we also can see that what will happen to the force, pressure on the wall. So if I say pi the pressure be the pressure at infinity, pi be the pressure at infinity, from our relation q we have seen q square is equal to 4m square y square by y square plus a square square. So m, that is q, at infinity the speed will be 0. So at any point on the wall, so that will be 0 at infinity, pi with the pressure, q square is this, at y is equal to infinity, this will be 0, because there is a okay. So then if it is 0, that means I will have p by rho is equal to p by rho plus q square by 2. If I go to Bernoulli's equation, I have pi by rho, and that means my q, my p is equal to, rather I will say p by rho equal to pi by rho minus q square by 2, and this is 2m y or q square by 2. So q square is 2, half is there, so we will get 2m square y square by y square plus a square square. So this will give me the pressure at any point the wall if I know. And again, so if the liquid is at rest, so if q is, again I will say, if q is 0, that means if the liquid is at rest, that means pressure at any point on the wall will be same as the pressure at infinity. So if the liquid is at rest, pressure on the wall is same as the pressure at infinity. Now with this understanding, if I want to calculate what is the force that is exerted on the wall due to the source, then I can always, because I know P, and then I can calculate the pressure, and the pressure from pressure I can calculate the force. So the force will be F is equal to rho, and this will be, you can easily see, this will be minus infinity to infinity, that is 2 m square y square by y square plus a square square dy. That will be the, so the source will be this amount of, and this, if we will calculate this, it will give us pi rho m square by a, because basically what we are doing is substituting for the pressure and integrating, and this pressure is per unit breadth of the wall. This force, this is force per unit breadth. This becomes the force. Again, if I have the relation Q, my Q is on the wall, my Q is 2m y by y square plus a square, and if I substitute, if I take y is equal to a tan theta, then this will give me y is equal to tan theta, that will give me 2 ma tan theta by a square sec square theta, and that will give me m by a sin 2 theta. That will give me the velocity. So if my wall is here, the point is here a, that is the point a and 0, then if this makes an angle theta with this axis, the point is here, this angle is theta, then q is m by a sin 2 theta, and it can be shield, and theta will be maximum, then q is maximum, q is maximum if theta is equal to pi by 4 plus minus pi by 4. This is pi by 4, and it can be seen if q is this maximum, then you can see that at that point the speed is maximum. We can see that p is minimum at that point. But theta is equal to plus minus pi by 4, because from Bernoulli's equation, once on a wall, on a boundary, if the speed is maximum, p has to be minimum, and this can be checked from the previous relation. So this is the way we calculate, suppose due to a source, how the force is calculated on a wall in a fluid flow. Now, with this I will go to doublet, because we have seen in case of a source or a sink, you have a source which are radial in flow is radial, and now if you think of a doublet, where as if we are thinking of two sources. So, let us look at what I mean by a doublet. So, now let us look at two things. I have a source of strength M. This is the point is minus A, this point is A, and here I put a source, and here I put a sink. So, what will be the complex velocity potential? And the two are at a distance 2A, source and sink, they are at a distance 2A. So, the complex velocity potential will be m log z minus A z plus A minus m log z minus A, and which I can write it as A log of I can put it z into 1 plus A by z plus m log minus m into log z into 1 minus A by z, and this gives me m log z. First term will be m log z, rather I will say m log 1 plus A by z plus or minus m log 1 minus A by z, because I have a m log z term here, m log z term here, they will cancel, and that gives me. So, what I will do, I will expand it. So, m, if I expand it in a Fourier series, Taylor series, then I will get it A by z plus, or rather the second term will be minus A square by 2 z square plus higher order terms here, then plus A by z minus A square by 2 z square plus the higher terms. This I am expanding in a Taylor series, and that will give me 2 ma by z plus the higher terms, because I am assuming my A is small. If I assume A is small, this gives me. So, now I look at two things. If my A is tending to 0 and the strength of source is tending to infinity in such a manner so that ma tends to a constant, 2 ma will tend to a constant, that is called mu, a constant. So, let me repeat, when there is a source, there is a sink, each is of strength m, and now I will just say that the source and sinks, they become very close to each other, whereas they become close to each other and the strength m will tend to infinity. So, in such a manner, so that 2 ma will give ma constant, and if that becomes a constant, then my W will be mu by z, and this is called a doublet. So, this W that represents the compressed velocity potential of a doublet of strength mu. And now if I look at calculate the what are the streamlines, W can be written as phi plus I psi, which can be written as mu x by x square plus y square plus I times mu y by x square plus y square, and which gives me psi is equal to mu y by x square plus y square. And if this is constant, if this gives me a constant, that means this will give me the streamlines, that is x square plus y square plus some 2ky is equal to constant. And we have seen a similar example in the last class, that this is like this. It will touch the x axis, the flow pattern will be like this. Of course, this is cylinder circular flow. So again the flow will be, the center will be, it will touch the x axis, and again a circular flow, the flow pattern will be, and this is the flow pattern due to a doublet. So from a source and sink, when they are placed together, particularly very close to each other, we will get a doublet, and the flow again will be, in fact we have seen such a thing when in our last class, if mu is equal to u a square, we have seen that when mu is equal to u a square, we have seen a similar example, that means when with w mu is equal to u a square, then w is equal to u a square by z, that we have seen this example, that it is a, like if a fluid is at rest and there is a cylinder of radius a moving at a speed constant, speed u naught, then this is the velocity potential. At the same time, here we are seeing that the same similar function, compressed velocity potential w, which is representing a doublet. But thus it is sometimes this example suggests that this constant value change the nature of the problem. There can be different problem, but by physical characteristics will depend on how we look at the problem and what are the values associated, the constant associated with it. So that's why in many situations we always, a similar problem can be expressed, rather a similar function can be used to understand the various flow characteristics, and all that will depend on that constant factor, the physical parameters that are involved in the flow. So that is one of the example. This is one example which shows that physical characteristics will change the nature of the problem. Often the compressed velocity potential is similar in nature. Okay, with this I will now go to another part of the problem, that is I will go to the Blasius theorem. And the Blasius theorem, so basically this theorem talks about the forces, component of forces that is acting on a body or on a boundary when there is a flow. Suppose let us think of, let a fixed cylinder be placed in a liquid which is flowing, the fluid is flowing irrotationally and steadily. And let W be the complex velocity potential associated with the flow. A fixed cylinder is placed in a liquid which is flowing rotationally and steadily. W is the complex velocity potential of the flow. Then let x and y are the component of forces and m be the moment on the cylinder. These are the force and moments on the cylinder, moments acting on the cylinder. Then if we neglect the external forces, due to the fluid, the forces acting on the cylinder will be x minus iy, and that will be given by 1 by 2 I times rho integral over c, that will be dw by dz square dz, whereas the moment m is the real part of minus rho by 2 integral over c, that is z dw by dz square dz. So this theorem, which when we have a fixed cylinder is placed in a liquid which is moving irrotationally, and if we want to calculate the force and moments, so x is the, here I can easily say that x is the drag force and y is the lift force, m is the moment that is acting on the cylinder. Now I will illustrate this through an example. Let me take the case of an example. Suppose I say my W is u z plus a square by z plus ik log z, and this velocity potential represents I have an infinite cylinder placed in a uniform flow and in the presence of and here I have a vortex, and the circulation k is the strength of the vortex. Then if I have to find what is the force, find the forces and moment that is acting on the cylinder. If I have to do that, then here W is given. What will happen to my dw by dz? My dw by dz is u 1 minus a square by z square plus ik by z. If this is, then what will happen to my x plus iy? If I put it in the other way, my x minus iy will be I rho by 2 into integral dw by dz square dz, and again which I can also write if I y plus ix as rho by 2 or minus rho by 2 integral over dw by dz square dz, and this, so if I expand this, so my dw by dz means minus rho by 2 dw by dz is u minus a square by z square plus ik by z square dz. So this is I have a circle, is a closed circle. So if I apply the Cauchy residue theorem, apply Cauchy residue theorem, so this will give me my y plus ix will give me minus rho by 2 pi I into, because I have at z is equal to 0 in the, I have a z is equal to 0, there are poles, so I can say sum of the residues. And only since we can see that in this problem the only residue is at z is equal to 0, and that is the residue, it can be calculated 2 pi I into 2I uk. And that will give me 2 cancel, I minus 1, it will give me, this will give me 2 pi rho ku. And from this I can always say that my y is 2 pi rho ku and again I don't have any, here my x part is 0. Further, if I calculate the moment by applying the same process, minus rho by 2, a real part of minus rho by 2 integral over c z dw by dz square dz, and I can easily find that this is 0. I am not going to, because this again can be applied by the Cauchy residue theorem, or rather say by Cauchy residue theorem, and this will be 0. So here we have a, this y part is this, so there is a, the present surface there is a lift force, but if x component is the horizontal force, vertical force is the lift force, and x component is the horizontal force, that is the drag force, that means there is no drag in this case, whereas the lift force is given by this. On the other hand, if you calculate the moment m, that is giving 0. Now this is a very classical example to calculate the force based on Blasius theorem. We have applied the Blasius theorem to calculate this. Now I will take few more examples in this class on this source and sink. Now suppose I have a source, we have seen that if I have a source and sink which are placed, we have taken two cases. In the first case, if I say that I have a source placed at minus, I have a sink, source placed at z is equal to minus a, and I have a sink which is placed at z is equal to a, and both are of strength m, then you have seen that will lead to a doublet. Now on the other hand, provided m tends to infinity, a tends to 0. On the other hand, if I suppose I say that, I don't say that this situation, suppose there is a, what will happen if I have just a source and a sink, both two equal sources. Here it is a source and a sink, source plus sink, it has given me a doublet. But what will happen if I have two sources? I think of two sources. Two sources, both are of same strength. Two sources of same strength. then my W will be m log z minus a plus m log z plus a, and that gives me m log z minus a into z plus a, and that gives me m log, that gives me z square minus a square, that is x square minus y square minus a square plus 2ixy z square will give me, and that will give me, from which I can get my psi. I will get my psi as, because m log r, so this will give me 2xy by x square m times 2xy by x square minus y square minus a square. So that means same as 2mxy by, rather it will give me tan inverse this, sorry. So my size tan inverse 2mxy divided by x square minus y square minus a square, and if psi is equal to constant at the equation of the streamlines, that will give me the streamlines, and if I further simplify this, then I will get x square minus y square plus, this will give me plus 2xy, I can say if I take m as 1, then I will get 2xy cot psi, or rather 2xy psi by m. I don't have to take this as, and that will be equal to a square. And if I simplify this, I can get, this is same as x plus y cot psi by m into x minus y tan psi by m. This is equal to a square. So if you look at this, they are nothing but it can be seen that these are again gives me rectangular hyperbolas, and some kind of rectangular hyperbolas. So what we have seen in the two examples, we have a, when we have a source and sink, we have a source and sink of strength m, rather two sources of strength m placed at distance 2a, then we are getting hyperbolas, rectangular hyperbolas. On the other hand, we have seen that we get a doublet if you take a source and a sink placed again same distance 2a, whereas the distance is small. So that is a, so what here I mean to say again, that just look at the, if you look at mathematically, the compressed potential W is equal to m log z plus a plus m log z minus a, and at the same time we are looking at the compressed potential W is equal to m log z minus a minus m log z plus a. So, if these two potentials, these two complex potential, they are little the difference is mathematically looking, there is only a change of sign in both the cases, only one sign change, but that leads to a flow which is quite different in both the cases. So, what we have here, so that always I suggest that simple representation of the flow by a complex number gives us very simple change in the flow complex number pattern, particularly gives us a very different types of flow, and physically it is quite very interesting physically to understand such kind of flows. And this has, in fact, this has because of this, in understanding of two dimensional flows, the role of complex velocity potential or the role of complex function theory cannot be ignored, because without much of a difficulty we are able to analyze several complex flows, and that is possible because of not only we are able to analyze the flow pattern, we are able to get the streamlines, even if as we have seen that using the Blasius theorem we are able to analyze various flows, particularly we are able to calculate the force and moments on a boundary of the flow, and this is what our Blasius theorem has given. So, in the next class again we will look into a detail about complex flow, various types of complex flow, and we will come to that. Particularly afterwards we will come to a little more about the conformal mapping, where how can we represent a simple flow. We can change the simple flow, a complex flow to a in one plane to a very simple flow in another plane, and in the process we will be able to analyze more complex flow patterns by using simple complex velocity potential, because we can transform from one plane, a complex flow in one plane can be transformed to another plane, where we can analyze the flow in a very simpler manner, and again we can go back to our new plane where the flow is very complex, and that is known as conformal mapping. In the next class we will talk in detail about conformal mapping and its application to several flows. Thank you all. Today we will stop here.